Okay, welcome to a short video on the reactions of alcohols for level 3 organic chemistry. I'm going to try and keep this short because a lot of these reactions tend to be just based on observations and experimental techniques. The first thing we did was we looked at distinguishing between the three types of alcohol. So distinguishing between primary, secondary, and tertiary. We'll take a look at that in a second. The next thing we took a look at was nucleophilic substitution on a tertiary alcohol, and this is experiment based, so we'll take a deep look at that, a detailed look at that. The third thing we look at we'll do a little section on amines, just as an aside. And the fourth thing I'll look at will be oxidation of alcohols. And from oxidation of alcohols, then we can have a short discussion on distinguishing between aldehydes and ketones. So we're just covering the section on the level 2, level 3 poster where we talk about primary, secondary, and tertiary alcohols, and then some of the reactions of those alcohols. So the first thing, as I say, was distinguishing between primary, secondary, and tertiary. So primary, secondary, or tertiary. That's the question we're asking here for the first section. So if I just remind you guys of how to distinguish between a primary, secondary, and a tertiary alcohol in terms of looking at the structural formula. The first carbon, which is directly joined to the OH group, I like to refer to as the central carbon. And if there's only one other carbon coming off that, then this would be a primary alcohol. So for example, ethanol. The secondary alcohol then is going to have two carbons joined onto that central one. So we could have this situation here, and then just a hydrogen here. So that would be a secondary alcohol. And then a tertiary, I just scroll down a bit, a tertiary alcohol would have three carbons stuck onto that central carbon. And the same nomenclature system applies to primary and secondary and tertiary haloalkanes. So it's all to do with how many carbons are stuck onto the central carbon. So our tertiary carbon will have, tertiary alcohol will have three carbons stuck on there. Now, how do we distinguish between those three experimentally? Well, it's quite a simple test. We made up what's called Lucas reagent. And Lucas reagent, we made that up using concentrated hydrochloric acid, so safety glasses are very important here. And then we just dissolved zinc chloride powder, ZnCl2 powder, in the concentrated acid, and that made up what's known as Lucas reagent. A Lucas reagent test is that it goes from clear to cloudy if a successful halogenation takes place. So what we're doing here is you're substituting an OH group with the chlorine from HCl. So if this reaction is successful, it goes cloudy. All right. So simple observations. Just divide this up. So this is straight from your poster, primary, secondary, and tertiary bubble for alcohols. So with a primary alcohol, there's no reaction at all with Lucas reagent. So no reaction, it stays clear. Stays clear. With a secondary alcohol, it will go cloudy after 10 minutes, and that's with heat as well. So it's quite a slow reaction. But with a tertiary alcohol, it's immediate. So based on this observations, you can see that the tertiary alcohol reacts faster than a secondary alcohol, which reacts faster than a primary alcohol. And this is just a simple test that Lucas came up with for distinguishing between primary, secondary, and tertiary alcohols. And why is that useful? Well, if you know that you have a mix of alcohols in a reaction vessel, and you just want to separate out the different alcohols and have just a tertiary alcohol to work with, then you could use the Lucas test. in conjunction with other experimental techniques. But once you have a tertiary alcohol, there's a lot more reactions that you can build upon that. And the second thing we looked at, which flows with the poster, is using a tertiary alcohol to form a tertiary haloalkane. This will be my second section that I'll look at now. This is a nucleophilic substitution on a tertiary alcohol to form a tertiary haloalkane. So that's the next thing I'm going to look at now. Okay, so a nucleophilic substitution on a tertiary alcohol to give you a tertiary haloalkane. Now this was an entire question in the 2010 paper, and it comes up quite a bit in other exam papers as well. So it's very important that students have a good understanding of this particular reaction and also the equipment that's used. If we write down a tertiary alcohol which came up in the 2010 paper, which was 2-methyl butan 2-ol, so I'll write down the name first. 2-methyl butan 2-ol. So the structure of that was as follows. OH group is on position carbon 2. And there's a methyl group there as well. And then there's a methyl group on the end. And then 2 other carbons in the chain to make it but. So we were looking at that reaction plus Lucas reagent, so it's plus HCl in the presence of zinc chloride. And then the reaction that you're looking for is a nucleophilic substitution where you're forming the corresponding tertiary haloalkane. So we're just going to use some colors here to highlight movement of reagents. So the chlorine from here ends up here. And then you still have the rest of your carbons in the but chain. Still have 4 carbons there. So this would be 2-chloro 2-methyl butane. So 2-chloro 2-methyl butane, plus you get a small byproduct here, which is water. And the water is being formed from the leftover atoms there, which would be the hydrogen from HCl, and then the OH group, which was substituted. So that's where that comes from. So this is nucleophilic substitution on a tertiary alcohol to give you a tertiary haloalkane. And I better explain what nucleophilic substitution is. I'm not sure if I covered that in my last video. Substitution. So a nucleophile, by definition, is a species with a negative center which is attracted to positive centers. So the nucleophiles that you need to know for level 3 typically are OH minus, and that's its negative center, Cl minus, and then you have the other halogen or halide ions rather. And then you have, doesn't necessarily have to have a full negative charge. It can be something like ammonia, which has 2 lone pairs, and that would be its negative center right there. And this is used to form an amine from a haloalkane, which is another example of nucleophilic substitution. So in our example here, we're substituting the OH minus nucleophile with the Cl minus nucleophile to give you your tertiary haloalkane. Now that's the chemistry behind it. What the exam papers often do is they give you a full question around the experimental technique and how you perform this, and we did this in class this week. We did the whole experiment. So I'm going to talk you through it in brief, and then we're going to point out the science behind each of the steps. So I'm just going to put down the steps and then link the science to it. So let's go. Step 1 in the experiment was you added your Lucas reagent to your tertiary alcohol in a separating funnel. I'll explain what that is in a second. Separating funnel, and shook it and shake. Okay, so separating funnel looks like this. Some of them are bulbous in shape, some of them are just tubular. So you can have that shape or that shape. In either case, there's a tap down the bottom, and separating funnels separate on the basis of differing density of the 2 liquids. So the more dense liquid will go to the bottom, and the less dense liquid will sit on top. And we'll discuss that in a bit more detail in a second. So the second step was you shook them and allowed to react essentially. So you allow your tertiary alcohol to react with the acid, which was according to our equation up here we just wrote. So you're allowing this reaction to take place inside your separating funnel. One safety issue with this is that there can be a buildup of gases, whether that be HCl vapor or H2O vapor, and you must therefore release the gas buildup frequently. Otherwise, that's quite dangerous for obvious reasons. And then also when you're opening the top, make sure that you don't have your eyes pointed directly at the any emissions. Alright, the second point here then was that after time, two distinct layers should form. Two distinct layers form, and it's going to look something like this then inside your separating funnel. So you have one layer on top, the left-hand layer on top, and you have one layer on the bottom. Okay, so the aqueous layer is more dense, aqueous layer, and that's what you want to discard, because remember H2O is a byproduct and we don't want that, and that's up there in the equation again. We don't want this, so we discard that, and it's more dense. And also any species which are polarized will dissolve inside your H2O and they'll be taken away with that removal. So two distinct layers form, the H2O layer or the aqueous layer down the bottom, which you discard, and then you should have a cloudy haloalkane layer, which is less dense, and that's at the top. Non-polar, generally referred to as being non-polar. So you have a non-polar layer on the top, and you have a polar layer on the bottom. So this is the separation that occurs in the separating funnel. So two distinct layers form over time. Number 3, you're then told to add sodium hydrogen carbonate of soda, aqueous, all right, and this is to neutralize. So the exam question will tell you the steps, but they'll ask you to explain why you do them. So you add the sodium hydrogen carbonate to neutralize any residual or unreacted HCl, because there may be some left over, so you don't want that. It's all about purity of your organic synthesis. Then the next thing they tell you to add is sodium sulfate, solid crystals of sodium sulfate, and that's to anhydrous. I meant to add there, anhydrous sodium sulfate. So anhydrous means, should spell that properly, anhydrous means without water. Anhydrous, without water. Okay, so if you add something like anhydrous sodium sulfate to a mixture, it will remove the H2O byproduct. So that's what the anhydrous sodium sulfate is for. And then the very final step is to perform distillation. So distill the remaining liquid, which is the cloudy liquid that's left in your separating funnel. So the cloudy stuff essentially. You want to distill that, and this is to separate the haloalkane product that you're interested in from any unreacted alcohol. And distillation separates two liquids, and I'll just do this briefly now because I'm going to cover it later in the lesson. But distillation is separation of two liquids of differing boiling points. So in this case, the haloalkane will have a lower boiling point than the unreacted alcohol, which has a higher one. So therefore, at the lower temperature, the haloalkane will boil off first. Then you recondense that and take it over the other side of the distillation equipment, and then you have your pure haloalkane, and then your residual unreacted alcohol is left over, still inside your reaction vessel. So that was all the theory behind the tertiary alcohol to a tertiary haloalkane. So quite a lot there. That was a full exam question, as I say, in 2010. So check out the 2010 paper if you want to see that question. So that's the second thing we did this week, another entire lesson. The next lesson was quite a simple, straightforward lesson just on amines. So if we take a look at amines, lesson number 3 this week was all about amines. Um, so amines were put onto the level 2 chemistry course last year, and so there's a nice little bit of crossover now between level 2 and level 3. Some of the reactions that you learned with amines last year are not up on the level 3 course, but we'll just cover them again anyway, because um, there's no reason why they couldn't put them on an exam question. The first thing is, how do you form an amine? So if we've just made a haloalkane, which has the functional group, let's just take it as a chlorine. So that's the haloalkane we've just formed with our process. What you want to do here is use ammonia, which is your nucleophile. Remember, it's a nucleophile because its negative center is accounted for by the 2 lone pairs, or rather the 1 lone pair. The solvent, though, which is dissolved and is alcoholic, and I'll explain why in a second. So something like ethanol. So ethanol is your solvent. And then from this reaction, you're substituting your chlorine nucleophile, your chloride nucleophile, your ammonia nucleophile, and you get an amine, which is an NH2 group stuck onto the rest of the molecule. And then we just looked at the 4 types of reactions on amines that you either covered last year or you need to know for this year. So just explain why it needs to be an alcoholic solvent, first of all. Well, if you remember, we just talked about the fact that if OH is present, then you can substitute that on a haloalkane and reform an alcohol. So OH could be introduced if you used water as a solvent, because water is constantly in equilibrium with its 2 constituent ions, OH minus and H plus. So if you use water as a solvent, you're running the risk of returning the haloalkane to its parent alcohol, and that is not an amine, which is what you're interested in. Whereas if you dissolve your ammonia in essentially excess alcohol, then you can't reform any more alcohol, and this is just Le Chatelier. Okay, so if you have excess product, the equilibrium will be forced back towards the reactant side, which is, in this case, we're interested in getting ammonia to substitute with the chlorine on the haloalkane to form your amine. So why use the alcoholic solvent? It's to prevent reforming an alcoholic product from the haloalkane. All right. So that's why. That's one thing you could be assessed on. And then these 4 reactions, as I say, simple reactions on amines. Basically, amines react just like ammonia. They're a weak base. So they react just like ammonia when you study that in level 2. They smell like dead fish. They definitely smell bad. So that's why I put a little fish on my poster when we talk about it. So if we just discuss them acting as a weak base, so an amine plus water, first of all, we use reversible arrows because that indicates that it's pure dissociation or not full dissociation. And a Bronsted-Lowry base, by definition, is a proton acceptor, so it becomes NH3+, and then the OH minus, that indicates that it's a base. That would turn red litmus paper blue. So that's a nice simple test for the presence of amines. With a strong acid, so we use a complete arrow for that. For example, HCl, you would get same thing again, NH3 plus Cl minus, and you can join them together. So you can also write that as R NH3Cl. So that would be a salt in this case, and that's known as the ammonium salt. Okay, so that's with a strong acid. With a weak acid, for example, ethanoic acid, so CH3COOH, reversible arrows again, because both of them are partially dissociating. You're going to get NH3 plus as usual, and then you're going to get your conjugate base. So that would be your conjugate base. Remember, conjugate base can act as an acid itself, could accept a proton, and in this case, this would be the conjugate acid, could act as an acid in the reverse step. And the final step, which is the only one that's really still on your level 3 poster, is the reaction of an amine with copper sulfate, aqueous copper sulfate. you're going to get the royal blue complex forming. Now, the way you remember this is just put the entire amine inside the brackets. And there's 4 of them, just need to remember that. The charge is 2+, which is attributed to the copper, the 1 copper ion complex to it, and then it's aqueous. And this is royal blue, so I'll use some blue to indicate that. Royal blue color or complex. Alright, so that's everything you need to know about amines, and then that reaches a bit of a dead end in terms of organic synthesis. So after that point we return to alcohols and we look at oxidation of alcohols. So that's our next lesson. So number 4, oxidation of alcohols we're looking at now. Oxidation of alcohols. Okay, so now we're going to take a look at oxidation of our 3 types of alcohols. So we've already talked about the fact that you can have a primary, secondary, or tertiary alcohol. Our primary alcohol, we're just going to take a look at ethanol. And we follow that the whole way through. Ethanol, right? Primary alcohol. And we're going to take a look at so for our secondary alcohol, we're going to take a look at methyl ethanol, which is just simply ethanol with the methyl group stuck in one of the carbons. And then for our tertiary, we'll take a look at dimethyl ethanol. Okay, so primary, secondary, and tertiary alcohol set up there. Now, strong oxidizing agents or oxidants, if you guys remember from your redox chemistry, would be acidified permanganate or acidified dichromate. So for the primary alcohol, we take a look at this first of all. Acidified permanganate, purple in color, or acidified dichromate, Cr2O72-, which is orange in color. I better write those above it. So this is purple, this is orange. Now the same oxidizing agents or oxidants we will use for each of these examples. If you oxidize a primary alcohol, you initially get an aldehyde, the aldehyde equivalent, which has this functional group right here. So that's the aldehyde functional group. And this would be ethanol. And if you further oxidize that with the same oxidizing agents, so acidified permanganate or acidified dichromate, you will get the corresponding carboxylic acid. So this would be ethanoic acid. Okay, and that's the carboxylic acid functional group right there. Now there's a little bit more to talk about, but I'll come back to that in a second. With a secondary alcohol, you can only oxidize it as far as forming a ketone. So using the same oxidants, either acidified permanganate or acidified dichromate, and you will form the ketone equivalent, which is going to look like this. And that's the ketone group right there. So that's as far, there's no further oxidation of a secondary alcohol beyond the ketone. And then with a tertiary alcohol, there's no reaction at all. So that's a good way to distinguish between the 3 types of alcohols as well. Just to talk a little bit about separating the aldehyde by distillation. And then I'll also talk about forcing this further oxidation to the ethanoic acid, the carboxylic acid, onto reflux. So let's just talk about those 2 processes now. So distillation and then reflux. So I'll bring this down here for a second, and I'll just look at the primary alcohol. So again, we went with ethanol. This is oxidation of a primary alcohol. So I also always say these videos are going to be short, but they turn out to be quite large. We cover this is a week's worth of teaching right here. So if we just use permanganate in this example, oxidize that initially, you're going to get the ethanol. This is ethanol. We go to ethanol, CH3, and I'll just show the aldehyde group there. And we further oxidize that, we will get the ethanoic acid. which is that right there. So the point I'm trying to make here now is that if we wanted to separate out the aldehyde at this point here, then we need to use a process called distillation. You may have come across this in junior science, and I briefly touched on it with the haloalkane experiment. What you need to do here is basically look at the equipment involved. So I'm going to draw out a simple distillate setup. So you have a pear-shaped flask, which is your reaction vessel. Then coming off that, you have a T-piece, because it's shaped like a T. And then you might stick a thermometer in just here. Okay, then probably the most important piece of the the apparatus is the condenser, but I'll come to that in a second. You're going to have a heat source here. All right, and as a result of that heat, you always get evaporation inside the reaction vessel. So E equals evaporation there. Evaporation happens there. In this case, you're going to have your primary alcohol. You're going to have your acidified permanganate or dichromate, whichever one you want to use. So your primary alcohol and your acidified dichromate. I'm just going to use some green here to show the formation of some ethanol or aldehyde. Now, what you want happening here is that you want the liquid with the lower boiling point to evaporate first. And an ethanol has the lower boiling point. Okay, and the point here is that the hydrogen bonding is possible for OH, the OH groups, or the it is possible between oxygen and hydrogen. So like the carbonyl oxygen bond and hydrogen between two ethanol molecules, that is possible, but it's stronger between two OH groups. So the hydrogen bonding in an alcohol is stronger, and that explains why the boiling point of an alcohol is higher than an aldehyde. So the aldehyde's boiling point is lower, and as a result it vaporizes. So I'm just going to represent that with some green smoke here. So it vaporizes first, and then what you want to do is you want to recondense that vapor into a liquid. So the next important part of your distillation setup is the Liebig condenser. There's a tube inside a tube, so that's not shown very well, but there's a tube inside a tube. This is your condenser. And the condenser, condensation happens here, and remember, condensation is from a gas back to a liquid, whereas evaporation was from a liquid to a gas. The condenser has a jacket of cold water which surrounds that inner tube. So the cold water is in blue here. There you go. There's cold water, and that causes the aldehyde vapor to recondense. And then you're going to collect that condensate in a little container right here, and you should just have pure aldehyde. So distillation, that process is carried out if you want to separate your alcohol from your aldehyde on the basis of the aldehyde having a lower boiling point because of less ability to hydrogen bond. And that's the process that you carry out if you want to separate the aldehyde out. If you want to continue the reaction further over to form the carboxylic acid, so if you alternatively want to force the aldehyde to fully oxidize into the carboxylic acid, well then you use the equipment slightly differently. A lot of the equipment is still the same, so you still have the same reaction vessel, so the pear-shaped flask. You still want the condenser, but this time the condenser is sitting vertically. So the condenser is sitting vertically on top of the pear-shaped flask. In this case, you're going to have a mixture of three different things now. You're going to have some of the primary alcohol, which may not have reacted. You're going to have your aldehyde, which is still in green. And then we'll use red for the carboxylic acid. So you'll have some carboxylic acid forming here. The point is that we don't want this aldehyde to escape. Right, we don't want that to escape this time. We want to force it to fall back down and react fully until it forms carboxylic acid. And that's the idea of reflux. So I describe this to students in class in quite a gross manner, but it helps them remember. It's like if you're having acid reflux from up in your stomach, and some acid comes up your throat, and you swallow that back down again. Okay, so reflux is the same idea. We have our aldehyde is trying to escape. Right, there's the vapor again. It has the lowest boiling point of all three. Carboxylic acids have an even higher boiling point than alcohols, because carboxylic acids can hydrogen bond both here and here. So hydrogen bonding happens twice in carboxylic acids, so they have the highest boiling point of the three, alcohol, aldehyde, or carboxylic acid. So the aldehyde is most definitely going to boil off first, but you don't want that to escape. So this is why your condenser is sitting vertically now, because the cold water in the condenser's jacket will cause that aldehyde to recondense and get back into that container and fully react until it forms carboxylic acid. So the ideal situation here is that you end up with a container at the end. I'll just draw this container, which has completely reacted to only have carboxylic acid only. And that's the idea of reflux. And that's how you would carry out this process. Okay, so there's two very important pieces of equipment, along with the separating funnel that we talked about already, and they're the three main pieces of equipment that you'll see come up on your assessments. Right, so the last thing now we looked at this week was, how do you distinguish between aldehydes and ketones? So aldehydes versus ketones, number 5, this is what we're going to look at now. We'll do it really briefly. Basically, aldehydes and ketones react differently, or can be distinguished rather, using either of two reagents. You can either use Tollin's reagent, or you can use Benedict's or Fahling's, it's also referred to as solution. All right, and both of these are redox reactions as well. And it's based on the premise that you can't further oxidize a ketone, but you can further oxidize an aldehyde. That's the premise. So you can further oxidize an aldehyde, like we just saw, to a carboxylic acid. You can further oxidize an aldehyde, but not a ketone. So that's the premise behind using these two test reagents. And the extent of what you need to know is essentially this. Well, first of all, we did this in class. We got you guys to make up the Tollin's reagent. Tollin's reagent was silver nitrate plus aqueous ammonia, and then we also had some sodium hydroxide in there as well, and then we used a bit of heat. And if it's successful, then you get what's known as a silver mirror forming. So the silver mirror forms in your test tube, and it does look really cool. Problem is, now I have about 6 test tubes from my lab sitting with silver mirrors stuck inside them, so I'll have to get those cleaned up before the holidays. But a nice silver mirror forms in the presence of, what is that doing? Get my pen back. Silver mirror in the presence of an aldehyde. The chemistry behind that, just for Tollin's, all you guys need to know is that, well, the Tollin's reagent, both of these reagents here are oxidizing agents, and so therefore they reduce themselves, and therefore you need to be able to write a simple little equations to show that reduction. So with Tollin's, since the main species we're interested in is the silver, you have a silver ion which is reduced with 1 electron to form silver solid, and this is what contributes to the silver mirror, and that's with aldehydes, and nothing with ketones. So that's reduction. With Benedict's, what you get is, well, Benedict's solution is blue initially, so you get a blue solution which goes red-brown, and this tends to be accelerated using hot water, so it often takes forever otherwise. Using hot water, again, only with aldehydes, because they can be further oxidized, whereas ketones cannot. And the equation you want to be writing here is copper 2 plus ions, so they're responsible for the blue color, going to copper oxide. And the oxidation numbers you have here, that's +2 going to +1 in the copper oxide, so there's your reduction right there. Again, reduction's taking place, and you just want to balance that equation out. So you balance your copper, then you add some water to balance the oxygens, and then you add your 2H plus. So that's the equation you want to be writing to show the reduction reaction of Benedict's solution to go from blue to brick red. And that's another test to distinguish between aldehydes and ketones. So that's everything we did this week. As far as I'm concerned, we've covered everything we need to for alcohols, and that brings us on to carboxylic acids, and then that's a whole other week's work right there. So we'll do a video on carboxylic acids next weekend.